Let's look at testing the null hypothesis that mu is equal to mu naught, and the question here is, should we be using a t-test or should we be using a z-test? Now, suppose we're sampling from a normally distributed population where sigma is known. This is going to be an important thing here. Normally distributed population, that's important. Whether we know sigma or not is also important. And we are testing the null hypothesis that mu is equal to mu naught. Well, when we are sampling from a normally distributed population and sigma is known, we have a z statistic, and z is equal to x bar minus mu naught over sigma over the square root of n. Now this denominator here we sometimes call sigma x bar, and that's sigma over the square root of n, and that is the true standard deviation of the sampling distribution of x bar. Now in the event the null hypothesis is correct, that z statistic has the standard normal distribution, I'm just going to call it SND, z has a standard normal distribution if the null hypothesis is indeed correct. Now, we don't typically know this value sigma. I do not typically know my population standard deviation, especially when I'm doing a test on the population mean. I'm not going to know sigma in the vast majority of situations. So what do? I estimate it with sample data, and I say x bar minus mu naught over, what am I going to put in here in place of sigma? My sample standard deviation, s over the root of n. And my denominator here I call the standard error of x bar, that is my s over the square root of n, and my standard error of x bar estimates the true standard deviation of the sampling distribution of x bar. But something fundamental has changed here. When I put s in place of sigma, s is a statistic instead of sigma, which is a constant if we happen to know it, and so this has changed, and this has something we call the t-distribution. And this test statistic, this t-statistic, this t-stat has the t-distribution. So I'm just going to put t-dist. Has the t-distribution, and the t-distribution has degrees of freedom, n-1 degrees of freedom. We've encountered this before in confidence intervals. So if you recall, the standard normal and t-distributions are both symmetric about 0 and bell-shaped. So if I were to draw this out, if this is my standard normal curve where 0 is in the middle, the t-distribution looks a lot like that. This is my z. Then the t-distribution is going to look a lot like that, only with heavier tails. So it's heavier tails and a lower peak. So the t-distribution looks a little bit like that. Now the t-distribution involves degrees of freedom, and those degrees of freedom are based on the sample size, n-1 in this case. And the t-distribution, as n tends to infinity, as your sample size tends to infinity, and your degrees of freedom therefore tend to infinity, your t-distribution tends toward the standard normal distribution. The t tends toward the standard normal distribution. We have investigated this in detail in confidence intervals. So, the t gets close to z when your sample size starts getting pretty large. So some sources go so far as to say that if n is bigger than 30, just use z. Forget you ever heard about that t thing. Now, I don't think that's the best way of going about things. So just pretend you didn't hear this side of things. Pretend you didn't hear this side of things. I don't think that's really the best way of going about things. So we're going to look at this in another way. Now suppose we want to test the null hypothesis that our population mean is equal to 100 against a two-sided alternative, and we get 35 values from our sample, and the sample mean is found to be 104 with the sample standard deviation of 12. Well, I could go and just run off and just do my test here, but we shouldn't just run off and crank some numbers without plotting the data. We want to plot our data first and have a look, because we can see all sorts of weird things, possibly, in our data. So let's look at it in this case. Here I've plotted out two things. Our normal quantile plot on the left, in which the points are on a very straight line, indicative of a sample being approximately normally distributed. So our normality assumption is absolutely fine for this data, and we can go ahead and use our tests based on a normal distribution. Over here, I've plotted our box plot, and the box plot I put in 100 on that line there, representing our hypothesized mean for a little perspective when we carry out the test. But the normality assumption is reasonable, everything looks fine, let's go ahead and carry out our test. So I want to test my null hypothesis here, that my population mean is equal to 100, against my alternative hypothesis that mu is not equal to 100. I do have 35 values here, which is not a tiny sample size, so the central limit theorem helps us out to a certain extent, but we've already verified normality here, so we're really good to go. So now the question boils down to, should we use a z statistic or should we use a t statistic? And I'm looking around. I don't see a sigma. Do you see a sigma? I don't see a sigma. So I don't have sigma. I have my sample standard deviation s, which means that I'm going to be using the test statistic x bar minus mu naught over s over the square root of n. And if I'm using s there, that means this is a t statistic. That means this is a t-statistic. And so I put in my appropriate values, 104 minus 100 over 12 over the square root of 35. And I get 1.972. And now I need a p-value based on that. and I go to a t-distribution and my degrees of freedom, I need degrees of freedom, n minus 1, 35 minus 1, 34 degrees of freedom. And I'm going to go out here, and here's my 0, and 1.972, and it is a two-sided alternative hypothesis, which means I need to take this tail area and double it. Tail area and double it for my p-value. And if I take that tail area from a computer, say, and if I were to double it, I would find for a final answer, I would get a p-value of 0.0568. That is my p-value, and I would make decisions based on that p-value from my t-distribution. Now just suppose that I screwed up. And suppose I said I'm just going to go to my standard normal table instead. And I went over here and got 1.972, and I followed the logic here, okay, if I went to my standard normal distribution and I said, okay, let's get that tail area, let's double it, I would find a p-value of 0.0486. Now, note, that's a little bit smaller than what we have up here. And it's actually, in my opinion, quite a bit smaller than what we have up here. And if we looked it up in a standard normal table, this would have been just flat out wrong. It would have been a little misleading, 0.486. This, from the t-distribution, would have been closer to the reality of the situation and the thing we should be using to make our conclusions. And you'll note, in this case, the difference is enough that our conclusions would differ. At the almighty alpha level of 0.05, we would have resulted in different conclusions. So really, if it is a t, if it should be a t, if you're sampling from a normally distributed population and the sample standard deviation is what you use in your statistic, if sigma is not known, then it's a t statistic, and you should find those areas under a t distribution. Now, as our sample size gets bigger and bigger and bigger, that normality assumption becomes less and less important to us. But we should still always plot out that data. And the central limit theorem kicks in, helps us out, and for larger sample sizes, we can use these methods even when our sample isn't quite normally distributed, but you should still always plot it out and have a look, and if we have some really strong skewness or outliers, we should deal with them. So always do your analysis the appropriate way.